Hello, welcome again. We are covering the topics Axial Flow Compressor for Civil Services Mains, IFS and GATE Aerospace exam. And in this uh, topic, we are covering subtopic elementary theory of Axial Flow Compressor. And here first we discussed the TS diagram, and then from that diagram we obtain the work done as W is equal to M Cp T naught 2 minus T naught 1, where T naught 2 is just transition temperature of air leaving the rotor, and T naught 1 is transition temperature of air entering the rotor. Okay, M is mass flow rate, Cp is your specific heat at constant pressure. Then we have drawn this velocity triangle. In velocity triangle, C1 is your absolute velocity at an angle alpha 1 at the entry of rotor, which has two components, CW1 and CA1. V1 is relative velocity at the entry, making an angle beta 1 with axial direction, and U is your rotor speed. And this is the outlet velocity diagram. C2 is outer velocity at an angle alpha 2 with the axial direction. C2 is having two components, CW2 and CA2, and V2 is relative velocity at the exit, making an angle beta 2 with the axial direction, and U is the dead velocity, that is same. CA1 and CA2 are same, U and U are also same for inlet and outlet. Okay, from these diagram, if you consider first diagram, then this is your U. So if we take this, then U minus CW1 by CA1 will be equal to tangent beta 1, or we can say U by CA1 minus CW1 by CA1 will be equal to tangent beta 1. And from this part we have CW1 by CA1 is equal to tangent alpha 1. Or if we combine these two parts, then we can write U by CA, because CA1 is CA, is equal to tangent alpha 1 plus tangent beta 1. Or we can say this whole U is summation of this and this. So this is your CA tangent beta 1, this is your CA tangent beta 1, and this is your CA tangent alpha 1. Okay. So U by CA is equal to tangent alpha 1 plus tangent beta 1, and for this is equation number 2, and 1 is for first one. Similarly, from the outer velocity diagram, so from the outer velocity diagram we have this part is your CA2 tangent beta 2, and this part is CA2 tangent beta 2, or U by CA is your tangent alpha 2 plus tangent beta 2. This is 2 and 3. Okay, and work done is W M CU CW2 minus, or change in work component multiplied by U. Okay, so that is your work done. So this is your work done. This is your relationship between angles and speed and axial velocity. Okay. So now we can put the value of CW1 and CW2. CW1 is your CA tangent alpha 2. CW1 is your, this is CW1, CA1 tangent alpha 1, and CW2 is your CA2 tangent alpha 2. So we can write it as MUCA bracket tangent alpha 2 minus tangent alpha 1. Okay. So now from the equation 3 and 4, these two are equal. So we can write tangent alpha 2 minus tangent alpha 1 is equal to tangent beta 1 minus tangent beta 2. Or work done have another expression, that is mu ca tangent beta 1 minus tangent beta 2. So this is in terms of velocity and angle, and in terms of temperature we have already found out this. So here uh, now these two can be equated, and from that the stagnation temperature rise T naught 2 minus T naught 1 or T naught 3 minus T naught 1 can be found out. So because T naught is equal to T naught 3, so T naught minus T naught 2 minus T naught 1 is equal to U m will cancel out U Ca by Cp tangent beta 1 minus tangent beta 2. Okay. So now this is the stagnation temperature rise. Now this is actual stagnation temperature rise, but if we consider isentropic process, then isentropic efficiency has to be considered, and this isentropic efficiency is T03 dash minus T01 by T03 minus T01. This is your T03 dash isentropic temperature rise, and this is your actual T03 is equal to T02. Okay, and in the same manner as we have found in centrifugal compressor, pressure ratio can be found. T03 by T02 will be equal to T03 dash by T01, and then this can be written as 1 plus T03 dash minus T01 by T01, and then this expression can be used. So it will be cycle efficiency into stage stagnation temperature rise divided by T01 is for gamma by. So here I will read out this. Assuming that Ca1 and Ca2 is equal to Ca, two basic equations follow immediately from the velocity of the velocity angle. U by Ca is equal to tangent alpha 1 plus tangent beta 1. Equation number 2. First we have taken. U by C is equal to tangent alpha 2 plus tangent beta 2, third equation. By considering a change in angular momentum of air in passing through the rotor, the following expression for the input to the stage may be deduced. So that is M W is equal to M U C A W CW1 minus CW CW2 minus CW1. And this W is equal to, in terms of angle of and axial velocity, mu Ca tangent alpha 2 minus mu. So in the previous expression, CW1 and CW2 are the tangential component of the fluid velocity, and after leaving and before and after the rotor. This expression can be put in terms of axial velocity and air angle to give this. It is more useful, however, to express the power in terms of rotor blade air angle beta 1 and beta 2. Then, because these are the imaginary angles, beta 1 and beta 2 are the blade angles that can be measured, and that is known. So we are putting this tangent alpha 2 and tangent alpha 1 in terms of tangent beta 1 and tangent beta 2. So then the work or power input becomes this. Next point, this input energy will be observed usually in rising the pressure of air and wastefully in overcoming various friction losses. But regardless of losses, or in other words, the efficiency of compression, the whole of this input will reveal itself as a rise in stagnation temperature of air. The stagnation temperature rise in the stage is given by T03 minus T01 is equal to T02 minus T01 is equal to U by UCA by Cp bracket tangent beta 1 minus tangent beta 2. This is equation number 5. The pressure rise obtained will be strongly dependent on efficiency of compression process, denoting the isentropic efficiency of the stage by eta is T03 dash minus T01 by T03 minus T01. The stage pressure ratio is then given by RS T03 by T01 is equal to bracket 1 plus efficiency into del T naught S. T naught S is this by T naught 1 is for gamma by gamma. So this is the almost the same thing that we have studied in the centrifugal compressor, and This is different